there we go. So embeddings. So this is a very similar graphic that I think the curriculum kind of shows. Is actually, I think, comes from, is this the one from Google's? Yeah, it's actually from Google's tutorial. Has a really great tutorial about like embeddings in general, which I have linked in here in the resources. But the real cool thing about it is that you basically take a word and you embed, this information about the word into a vector. And so what's kind of cool is like you can see them as points here. So you can think of vectors as either kind of like an arrow going from the origin to this point or just the point itself. And what's kind of cool is that you can create these embeddings which have some kind of contextual information, and that will be converted into a mathematical object. But what's really cool about this is that you can start doing things like basically moving across this. So you can see this example here where it's saying like we have king and man and you shift it off in the same direction. You get like, for example, gender information. So like a shift from this direction actually represents gender information. You can also see here like walking to walked, swimming to swam. This would be representing something like, verb tense, is it the present, is it the past or something like that. Here's really cool is that you can see something like, Turkey, Canada, Spain, and then shifting it over, this might represent like country to capital, right? So what's really cool is like, oh, that's really nice to kind of have this, like you can just shift everything over and you know what that's supposed to represent. What's really cool about this is that you might say, well, okay, how do we get to this point, right? How do we get to this point where we can actually shift over? And that's what's a really cool thing is that you can do this automatically. Basically, the idea is that you do a machine learning algorithm that will say, figure out the context of this. And the reason why we can actually do this is something called the distributional hypothesis. I kind of linked it here because I don't think the curriculum mentions it. But basically, the idea is that words that are related or have context with each other are closer together in sentences. So you will tend to see the word, let's say Moscow, close to the word Russia. But also, you might see Moscow and Tokyo and Berlin and Rome. Those might also be used closer together than other city names. And that's because they're all capitals. So you tend to say, if they are in a text that's close, like those words occur close in the text, they're related in some contexts. And so that's actually what we'll use this idea here. And that's why we're able to actually build up these word embeddings. Because basically the reason why these exist is because we know what direction they're in, basically where they exist in this multidimensional plane. Okay. Hopefully that wasn't too just like, I don't know, hand wavy, being like, oh, they just live on this multidimensional plane. But the main idea here is that it can encode this information. That's why we call it embeddings. They're embedding this information into this vector. Okay. So I have a couple of resources. So one quick thing, I used to point to this Kaggle tutorial on embeddings. Kaggle has like kaggle.com/learn. They have a few like tutorials, very few of them, but they're pretty good. They had a tutorial on embeddings, but they kind of just like removed it from their thing, so they're referenced to it. But the Kaggle kernels are still there, at least as of right now. I think it was from a data scientist, Colin Morris. He does a great job of actually explaining these things. I've looked this through. But also there's a Google embedding course, crash course, like I mentioned, where I think this is where this, what's it called? This image came from. And that's a really great thing that you can just walk through. And it does a really great job of explaining it and showing it. I think it even shows it in TensorFlow. But the main idea is that you can use things like neural networks to basically build a good embedding from here. And it's actually really smart the way it works. It was first developed, I think it was first developed by Google back in 2014. So like, it's like 5 years, well, I guess 6 years now, almost, 2020. But it was developed not too long ago, and it's a really useful thing. But to kind of show you a little bit what embeddings can do, like how you build this, I'm just gonna point really quickly to this notebook. So in this notebook, note that embeddings, like we're talking about word embeddings, but you can do it with a lot of different things. So for example, in this example, I think in this tutorial, they actually use movie ratings to build up this embedding set. And the idea here basically is that you can say, go ahead and build up this embedding by using machine learning and saying, hey, I want you to encode, this, movie with these movies into a smaller vector. So the idea here is like, this movie, whatever this movie, oh, this case, Legally Blonde, is represented by these 8 numbers. And those 8 numbers would represent something about the movie, and that you can compare these different movies by looking at their vectors. And so if you remember this, like, I can't remember where I mentioned this before, like what lesson we talked about it. But like you can think of this like, oh, this represents how much comedy, you know, is in this movie. And this can represent something like, you know, how much, you know, I don't know, like drama there is in the movie or something like this. And then you have other, maybe other values in there can represent something like, you know, oh, is it a romance or something like that. And exactly what those different columns are is kind of irrelevant. It doesn't really matter what those things are. It's just that there's some inherent thing about the movie that exists. And the idea here is that they actually use, instead of using how close the words are to each other, like we're going to do, they actually use what users liked what movie or what users rated each movie. And that builds up the context. And the idea here is that a person can, you know, give information, some context about what these movies are. And then we can take the sum of all of the users' input, basically all of the users' ratings in the movies, and build up this kind of encoded, this embedding. So this encoded vector with some information that we can then compare. And we'll kind of show you a little, I'll show you guys a little bit later, but like one thing you can kind of do then is do kind of similar stuff with kind of using this like after you build these embeddings, and you can actually pull out extra information. So one classic one is actually visualizing this. And so down here, for example, they show all the documentary movies. And what's kind of cool, you can see all the documentary movies are kind of clustered together. Remember, these are all just kind of like vectors. And you can start doing things, for example, this is comedy, drama, romance. I know it's kind of small and it's kind of hard to tell with these colors, but you can see like drama tends to occur like over here, where comedy in this kind of yellowish kind of color tends to occur over here. And you can see romance, there's some pockets, but there might be some more like romantic comedies over here, or there's some drama comedies and stuff, or drama romances and stuff like this. So you can start building up a picture of like where these kind of crossover and where they kind of exist. So anyway, that's kind of like what you can do with these embeddings, and you can get some information. So basically the main thing I want to emphasize is embeddings basically encode this context about, in this case, movies, but we'll talk about it in words. So the words will actually encode, the embedding will encode some information about the word. Okay, so let's get into a little bit like how we can actually build this. Or I guess first, is there any kind of like overall questions of exactly what I mean by context and like meaning in here? Okay, cool. And I think it will make more sense as we kind of go through to say like how these are built. So the first one that we're going to talk about is like word to vec. And so word to vec is a really powerful machine learning. I think that's one of the original ones. And the idea here is we can actually do something called a skipogram model. So essentially what we do is, remember how I said this embedding is going to be based on the fact that words that are close together will mean or have similar context to each other, right? So the idea here is that you have a one-hot encoded of like all the different words. So let's say you have like 10,000 different words. That's a really, really big vector on it. And that's going to be really difficult to actually make any predictions with, because the machine learning model is not going to know what the difference between, you know, fox and dog. It just knows that this is fox and this is dog, but there's no relation exactly what those mean to each other. So what you essentially do is you take a neural network, a multi-layer perceptron, MLP, right? And you basically say, all right, here's all of the words, right? And then on the output on the side here is basically you're going to try to predict where, how do I say this? The probability that the word is going to occur within like, you know, 4 words around it. So the idea here is that you want to train, if I take the word dog, what's the probability that the word jump is going to be around it? What's the probability the word cat is going to be around it? What's the probability of the word, you know, house is going to be near the word dog? So the idea here is that we have these kind of like words here, this one hot encoding, and then on the side here's the other one hot encoding of the same words. So these are like, for example, 10,000, like a vocabulary of 10,000 words would be a 10,000 input and a 10,000 output. Okay. And so what we're really trying to do, if I were to kind of like draw this out a little bit, or, you know, I'm going to type because it'll take me longer to actually type it out. But if I had like the sentence, you know, like, or like if I have the word, the dog is very brown, right? Is that I would say, okay, like within like 2 words of each other, you know, what words occur within like, you know, near dogs? Like, okay, well, brown occurs near dogs, you know, assuming I kind of like get rid of stop words, stuff like that. And say, okay, like brown occurs, you know, frequently around dog. And basically we just say, okay, this is going to built up a little bit of the probability, like this target here. It's just counting the frequency of how often this word occurs near the word dog, and then near the word cat, and then near the word, you know, house. And you do all this for all of the words in the corpus. Okay, does that make sense to everyone, how we're building up this probability? Okay, I just want to make that clear. So again, this is kind of like the frequency of these words occurring to this input word. So if this is like the word dog, this is like 0, 0, 0, 0, 1 means dog right here, and then all zeros here. I feed this into a neural network. I have this kind of hidden layer right here. In this case, you can see it's a 300 node layer. So it just doesn't really matter exactly what the numbers is, but like there's 300 points here. You pass it in here and say, what's the probability that these other words are? Well, ant very rarely occurs when it's dog. Zoo, a little bit higher than, you know, and barber, like almost 0. Like there's never, dog and barber are never mentioned together. And so what's cool is that you then say, okay, let's train this, right? And basically you optimize it, right? And what's kind of cool is that if you have like this input layer, this output layer, and then this hidden layer is going to essentially encode information about how this word over here, let's say dog, this dog is related to these words, and it's going to encode this extra information. So what's really cool is that we don't really care about it making predictions. All we really care about is basically teaching it the context. And that context is going to be represented by the weights that are in here. So then what we can do, once this is fully trained, you know, basically it's pretty accurate in like predicting what the frequency is based off of these values. We can take the values from here and say that is what represents dog. So I put dog in here, which is like all zeros, like let's say 1, 2, 3, 4, 5, 6, and then 1, and then all the rest are zeros. This would encode into a smaller vector. So instead of having a 10,000 vector long, you know, representing dog, you now have something that's 300, and they're going to have some values in there. But the idea here is that what's going to happen is that words like a fluffy dog is a great pet and a fluffy cat is a great pet. This dog and cat are more or less interchangeable, so they have similar context to each other. So you can see that words that are close by are going to occur frequently around the same words of similar context. Okay, does this make sense? What's going on? How thumbs up, thumbs down, sideways? Okay, I see thumbs up, cool. All right, so the main idea here is that basically we're tricking the neural network to make these embeddings for us and say, all right, basically find the context, and that's what's going to be in this vector. Now, each of these words will now have a vector of context, which we call the embeddings. And now with the embeddings, we can do all the really cool stuff with features and stuff. Okay, so that's one. Oh yeah, go ahead.
You always have to use just one hidden layer, or can you use more?
So you can actually use multiple hidden layers. So I'm trying to show an example of this. Sometimes you can even use but we'll talk about recurrent neural networks. But the main idea here is that because we're squeezing the information down and then it has to output here, this layer has to encode, like essentially has to keep extra information somehow, has to kind of condense, kind of compress this information. I'm trying to think of a good example of this, but like basically you're trying to like squeeze everything down, and like it has to fit well enough in here. So basically it's condensed information, but you could technically have multiple hidden layers to do this one thing. But you could also have just one hidden layer as well, and that can be just as good. Okay, and that's what Word2Vec is. Word2Vec, we actually look at the curriculum, they show you how to like implement this. Word2Vec really is just the model, and basically you can take in your corpus of data and feed it in, and actually it will train the model for you essentially, and will basically pull out this information, and that's just a model that works really well. Okay, cool. So that's one way to do this, Word2Vec. Another example of kind of like how you could do this is GloVe. So global vectors for word representation, but basically GloVe, right? That's how everyone calls it. And basically what this is doing is that you have essentially kind of the same idea. You have words, and then you have like the context. And if you multiply these together, you would get this coherence matrix, which is kind of like what we talked about, saying how frequently does the word appear in the context of this other word, which just means like, oh, if I use the word dog, how often is the word fluffy used? How often is the word brown used around that word? Okay. And so what's kind of cool is like, if you think about this, if we have those words and features, we actually can build this up really easily, basically saying how frequently do these words happen, and each, like you can think of like the features being like, you know, the one-hot encoding. We actually can build this, but the feature to context, exactly like what is the context, it's not easy to build up. But if we have these two matrices, we can put it together and figure out and predict basically how frequently other words occur this other dog. So what's kind of cool is that what we do here is say, well, okay, if we have this word I, basically this word I represented by a vector, this word J represented by a vector, and multiply together, we would get the probability that I occurs such that J is around. So if you think of like the word like dog and then the word fluffy, it's like the probability that the word dog occurs near the word fluffy. Okay. And so it's kind of cool. We can actually say, okay, we can then actually train this, say, okay, keep adjusting the different values in this feature context matrix, which we don't actually know how to, like, we don't know what this is, but we could keep kind of like tweaking it. And if we could do that and get it pretty good where we know this part, we know this part, if we can figure out like something that gets really close to these values, then we can actually develop this feature context matrix. And again, we use a neural network essentially to do this for us. And basically we're just trying to get it closer and closer. So the problem with this is that if you adjust one, you're probably going to affect a whole bunch of things. And that's why we use machine learning algorithms, that basically it can do this optimally by doing gradient descent to try to get closer and closer and closer to that value. So at the end, what's really cool is that we actually get this matrix or something that's close to that matrix. And then these features right here, well, those features are going to just be like the vectorization of the word, which is the embeddings. So just another way you can implement this. And again, it's just showing you like context, like what this is doing. But to implement this, it's much easier to actually call this over, like to actually implement it. Okay, cool. Sound pretty good? All right, cool. So once we have these like embeddings, whether it's Word2Vec, Glove, or some other process we do, right? We can actually do some, actual like analysis with this. We can now, we've essentially built up context into these embeddings, and now we can actually use that context, use the embeddings to pull out that context or kind of look at interesting things. So I always mispronounce this, how people pronounce it, Genism is a library. Basically, we can take this guy, and this actually does a really great job of actually showing, not showing, but kind of like exploring a little bit the feature set. So you can see things like how far are these points from each other, or you can kind of show a few extra things. So I'll kind of show you this in this notebook. But you can see here, this is really easy to implement with Word2Vec. So you can see here, this actually comes from the library here. We import Word2Vec here, and then we actually just pull in this data, assuming that we get it all tokenized and everything like that. This size right here is going to be how big is our embedding. Note that our embedding tends to be the size of like hundreds, but that's going to be much smaller than like thousands, right? Or tens of thousands of words. So, you might see something around 100 to maybe even 500-ish, depending on your corpus. And basically those are these different parts, like workers, for example, just optimization, saying how many CPU workers you're actually going to use to optimize it and stuff like this. And they train it, and then you have your vector, hopefully. And then once you have this, you can actually kind of check this out. So, I couldn't remember which one it is. Here it is. So this one kind of assumes like, all right, we trained our embeddings, we got our embeddings, you can do something on here. So this again uses the movie context. So you can do certain things like, for example, what's ones are most similar to Toy Story. So you can kind of think of this as being like, the way you do this is just saying, what's distances? Like, what are the things that are nearby it? So for movies, it's like, oh, what's the most similar movie? For words, like, what are similar words? So for example, if you say like dog, what are words that are similar to dog? Well, cat might be there, but also things like maybe like Chihuahua or, German Shepherd or something like that. Those words might appear as well because they're similar to that word that you feed. So you can see here, it's similar to Toy Story, are Toy Story 2, Toy Story 3, Finding Nemo, Monsters, Inc., Bugs Life, which all make sense. These are basically all like Pixar movies, right? And note that this was never told that this is a Pixar movie. It's just kind of figured this out essentially by looking at all the user information. Basically, we embedded this information into Toy Story on the vector. But you can also do some really interesting things. So for example, this is like semantic math. So whenever you see this movie, or whenever you see movies, think of just, you can replace it with words, okay? So you can see here like Scream is equal to Psycho plus something. So you can think of like, what movie, if you combine Psycho with another movie, would give you Scream, right? So you can kind of think of like, well, Scream minus Psycho, what kind of movies would those be? And you can kind of see like, okay, what is that going to be? In this case, it turns out like Scream 3, Scream 2, not really that interesting. Piranha, Freddy versus Jason, Final Destination. But then you get things like Booty Call, Charlie's Angels, Mortal Kombat, Deuce Bigelow, right? And you're like, all right, what's going on here? And the kind of like Colin Morris here puts in, says, oh, like Scream is kind of like a scary movie, but kind of like funny or campy kind of deal. Like it's kind of got that like comedy in it. Psycho's pretty a pure horror part. If you remove the horror out of the Scream movie, you get comedy, and that's essentially what's going on here. So you can kind of think of it like, he shows an example of like analogies like in language, but you can do the same thing like with like words and stuff like this. So it's really interesting kind of like tutorial that kind of talks about embeddings. I think the movies actually make a lot of sense. Where like, oh, I can kind of see where the similar movies are in here, but you can apply it as well to like words. Okay. So the last part is kind of like this visualization. So like one thing is that your embeddings are going to be, let's say 100, 100 dimensions, for your word embedding. You can't visualize this easily what this is. So t-sne or t-sne, this basically allows you to project something down. It's like a dimensionality reduction. Project something that's very high dimensions and preserves the, what's it called? It preserves the distance between different points. So if you imagine these points right here, if you imagine like, let's say 100 dimensions or something like that, you can't easily show that without slicing it up 100 different ways, or I guess not even 100 different ways. It has to be like 100 by 100 ways, right? And so you can kind of see like, okay, this is gonna be a huge part. t-sne basically does a thing, and if you want to know more mathematics, you can definitely look it up. But the main thing you have to know is that it projects it down, and the main thing, it doesn't keep shape, but it keeps the distances from points. So what's kind of cool is that, well, for words embeddings that similar words are close by each other. So you actually get these groupings together. So this is good not just for embeddings, but can also be really useful for other multidimensional, like data sets and stuff like this. So I kind of mentioned this. This actually picture comes from one of my favorite books, Hands-On Machine Learning, right? So you can kind of check this out. But just to kind of show you again, like that example from this Kaggle tutorial, they kind of show you again, like if you imagine these are all the movies and they're all these embeddings, but in this case, it was like 8 dimensions, right? And they projected this down into 2 dimensions, right, for t-sne. And you can see here, like there's definitely clusters and stuff like this. And then you can start doing things, for example, he looks for everything that's called Harry Potter. And you can see all the Harry Potter movies and be very close together, which, what do you expect? But you can also see other movies that are close by Harry Potter. For example, the Hunger Games. And you can kind of say, oh yeah, I can kind of see how Harry Potter and Hunger Games, they're not exactly the same, but they have like that similar genre, maybe series, kind of focused more towards, teenager, kind of like that age group. Also, kind of get the same feel for it. So you can get the idea of like, oh, these are very similar word or movies to each other. And then of course I showed you a little bit like documentary. Basically there's more of these clusters in here. And then you can see things like overall patterns for like comedy, drama, and romance, which for the record is that when you first feed this, when he built these embeddings, they didn't put this information there. They didn't ask which movies are comedies, which movies are drama, which movies are romance. It's just that the fact that movies, or, this, we could talk about words, but movies and movies are similar to each other when they're, or movies that are close by each other in the embeddings are similar to each other. So that's why you're able to preserve this kind of information. And know that technically this is an 8-dimensional set and we kind of reduced it down, but the distances are preserved. Okay. So that's kind of like the overall of like how this kind of works. And this is a good way to kind of like see, like, for example, if you're looking for words that are very similar to each other, and you can do things like I showed, like, you take the classic is like king and queen, and then you subtract off, basically you move off in gender, you get man and woman. So you can do some interesting things like this. Note, however, those are based off of similarity based on your corpus. So it's a really good example of this is that we talked about like, these country capital. This doesn't necessarily mean it will actually find the capital. It might just be the thing that people talk about the most. So if you kind of move in this direction, you might see like, oh, Spain goes to Madrid. You might see Japan go to Tokyo. But you might see like, let's say the US, like let's say they have the USA here and we move the dot in that direction. It might not say Washington, DC. It might say New York. And New York might be like, it's not that it's the capital, it's just like the thing that is usually mentioned around other capital words. So something to be aware of, that it only knows the context based on what you feed it. So it's always going to depend on your corpus. Okay. So those are a few things you can kind of do with embeddings and stuff like that, especially visualization for t-sne. And then you can see I don't know. That's how I kind of like, you can explore a little bit and see like similar words and similar, contexts and stuff like this. Okay, cool. Any questions about these two parts, or really anything that we kind of just went over?
So I'm guessing what you can do with that depends a lot on what you can feed it, right?
That's right.
Like you can get completely different results depending what you're using. Is there like, I don't know, in the field, there is a common sense on what to do, like the more the better or something like that?
Yeah, in general, the more the better, because you have more things to pull the context from. Note, however, this is actually a real thing. I remember it was like last year, there was a linguist that was having a talk about, natural language processing and like data science. And they were talking about that a lot of the data sets that they were using did not include minorities or, like basically non-whites. And what happened is that the context of like, I think they were using it for, I think it was really for Twitter data. They found that basically the predictions from NLP did a fine job for what, maybe like for that data set, who were not basically like, I think she specifically talked about like the Black Twitter essentially, which is kind of like, oh, this other kind of like culture of essentially like how they talk and stuff like this on Twitter. And it was misclassifying a lot of the sentiment analysis in there. And so you should always be really aware of like, what is the corpus that I'm feeding my data set in? This is true for any data set, right? But like in this case for natural language, like what is my corpus and what are the things that it's going to be used for? And so you should always be aware of that kind of background. Like it's really tempting to use like a pre-made, like, using a corpus and using that information, but always know the context of where that corpus came from, where this model came from, and know how it's going to be used. And that's actually a really important thing that, again, it's kind of like building up features and stuff like this. So if you are going to use something like, let's say you're like, oh, I know it's going to be used for this, certain case or whatever, know that you should probably, as best you can, use information from that, wherever that corpus is kind of like originating from, and that will give you better results. However, note that you can still do things like, I actually forgot about this part, transfer learning. You can actually use something that you've already previously learned that's similar enough and use that information to help train your stuff. You might still need to modify it slightly, but you can do a decent job, but just being aware of that context. Does that make sense, Shivana? Good question, by the way. So yeah, just know that basically for embeddings in general, you generally have this overall like hundreds of dimensions, but you can actually use the embeddings you learned before, but just know, like I said, like specific terminology, context, make sure that's going to carry through. You obviously wouldn't use a word embeddings for English and try to apply it to Spanish or some other language. It just wouldn't work, right? You would contextually understand that, but also know like proper, quote unquote, proper English, which I really hate that word because there isn't really like an official, like, how you're supposed to speak English. But if you have information from, or corpuses from different areas, it might not be the right thing to to use that embeddings are already built up. You might have to think, oh, we need to retrain this on this corpus. Okay, cool. Yeah, so that's kind of word embeddings in general. Any questions at all about this part? Pretty good. Okay, so I think they're really the coolest thing because it's like you basically automatically get context out of just training it and building up these word embeddings. So the last thing that I want to bring up is sequence-to-sequence model. So I know we only have about 7 minutes. Are you guys okay if we go a little bit over?